Okay, hello. My name is Matt McMullen. I'm your host today. I just want to run through some housekeeping items. The emergency exits are out the doors and to your right. The bathrooms are out the door and to your left, and you should find them on the left-hand side. Just a reminder to please submit your feedback on the sessions in the app. Please put your devices on silent, and a reminder that all sessions are recorded and will be available after the event. So for this session, building a critical communications platform using serverless technologies, please welcome your presenters, Doug Gartner and Max Stevens.
Okay. Welcome, everyone, and good afternoon. So today, we're going to be talking about, whoops, let me go back. We're going to be talking about building a critical communications platform using serverless technologies. So essentially what that means is we have a customer, Spoke, who worked to build this platform using just serverless, went from a journey, essentially from a monolithic application to serverless. We're going to go through some optimization strategies on how you want to do that, and then we're going to go through some lessons learned. So just a couple of quick items. There are two sessions that are kind of related in the serverless track. One is to infinity and beyond, so they're talking about what's new with serverless. And the other one is built and delivered in 6 months using serverless technical patterns and microservices. So two other good sessions to check out. If you can't check them out here, I encourage you to watch the recaps afterwards. So quick agenda, we're going to do a serverless review. I won't spend too much time on this. This will be just 5 minutes review of what serverless is. Then I'm going to talk about some Lambda best practices and optimizations. From there, we're going to introduce Mac from Spoke, and he's going to talk about the journey to going 100% serverless, as well as a serverless orchestration deep dive, and then some of the lessons learned and gotchas along the way. So a little bit of review here. So what serverless is, it allows you to get closer to that efficiency curve. So instead of provisioning, let's say, an EC2 instance or a machine that you have to have running all the time and that's kind of sitting idly, you don't need to do that, right? You can just spin up what you need when you need it. And this is really good this is the best way to get closer to paying for what you use and for paying what you consume, as opposed to spinning up these machines that may sit 60%, 70% or higher idle throughout the day, and you're sort of paying for those CPU cycles and you're consuming them without actually benefiting from them. Again, there's automatic scaling built into serverless. So in terms of previously, you'd have to build out your own scaling mechanisms. You'd have to make sure that you're planning accordingly such that when you receive bursts of traffic or new traffic, you have to scale accordingly. But using serverless technologies, that sort of automatic scaling is built in. And it's a really good way of getting, again, closer to matching that demand and matching that efficiency curve. And then lastly, it's highly available and secure. So again, traditionally, you would have to build your applications to leverage some of the high availability best practices, which is still a good thing to do. But here, a lot of that high availability is built in. It leverages multiple availability zones. And it's secure, and you get to inherit all of those controls as you build out your applications. So just a kind of a covering of some of the serverless capabilities, services that we have. Things in the integration layer, things like API Gateway, Cognito, SQS, or the Simple Queue service. These are great ways to leverage compute, leverage integration services without actually spinning up servers to host these things. Data stores, so S3, if you need object store and you need just sort of a catch-all to place all of your objects, S3 is a great way to do that. Aurora Serverless, if you have a use case that warrants the traditional sort of relational database and you need to have that, you can still do that in a serverless way using Aurora Serverless. And then DynamoDB, so this is a NoSQL serverless capability. If you really just need a key value store, right? I just need a place to put my keys and values. This is a distributed key value store that allows you to do that. And Mac is going to go into some of the best practices and deep dives on what they learned as they went through that journey. Then at the top layer, we have our two compute services, so Lambda and Fargate. Today, we're going to focus on optimization strategies for Lambda. As you can imagine, when you're building a critical communications platform, latency means everything. It means a lot. And if you have seconds of latency, those seconds of overhead are really negative in terms of impacting your overall experience, and the critical communications that need to be delivered in a time-sensitive manner. So we're going to talk about some of the optimization strategies that you would use on Lambda to really make that latency get as small as possible, so that you don't have these hiccups in delivering your messages. So from a development standpoint, Lambda does a lot of things. It's easily accessible for developers. It supports all runtimes. We have a lot of these runtimes out of the box, things like Java, Node, Python, all out of the box. Go, other languages. It's ISO, PCI, HIPAA, SOC, GDPR, and FedRAMP compliance out of the box. So you can inherit all those controls as you're building out your compute, your serverless compute, as you're building out your application space in Lambda. It allows for greater productivity. So there's toolkits already available for some of the popular IDEs. So if you use VS Code or IntelliJ or PyCharm, you can use and leverage those toolkits that integrate with existing IDEs. And it's a simplified deployment environment with these applications and IDEs. And then lastly, there's new application patterns, and these will continue to iterate. We support up to 15-minute functions for running in Lambda. You can use SQS for Lambda, automatic load balancing, and then support for Kinesis data streams enhanced with the fan-out approach. So these are some of the new patterns, and I'll talk about some other new initiatives and other things we have going on. But essentially, you can think about this as a really easy way to get going, get started, but still scale and continue to iterate as we add more capability. So again, going back to this idea of optimizations and best practices, if we think back to the critical communications platform, the idea is you have to get these messages delivered, you have to push them forward, and what you might think is I should have a capability sitting idly waiting to deliver the message, and that's going to be the most efficient way, but you don't need to do that. You don't need to be sort of that wasteful when you're thinking about delivering these messages. So let's go through what an actual occurrence of the Lambda lifecycle is. So to start, you have to launch a container. So these Lambda functions, this code that you've written is going to launch inside of a container that needs to be executed. So that's going to go through a bootstrapping process. In that bootstrapping process, you can think about all of the initialization that you would normally need to do in your traditional application. Still needs to happen here, but you're trying to make sure that bootstrapping is as lightweight as possible and as accelerated as possible so that it's delivered to, your messages get delivered as quickly as they can. Then it goes through the execution phase. So this is where your business logic actually gets executed. This is like the core of the function. And so all of the other stuff above that you can think of as overhead. And that's what you need to minimize to get to that business logic, to execute that business logic. From there, once it's executed, it's completed, the message has been sent, whatever operation in your Lambda function, whatever business logic you put in there has been delivered. And so then it goes into sort of a waiting period, right? It goes into a freeze state. And then when you need to bring that back in, when an event or a trigger criteria comes in to spawn that new Lambda function, it has to be thawed out of that. And so once it's thawed, then it goes back in, it has to bootstrap and do all of that good stuff. So again, the execution part you can see here is a really small piece of this life cycle. And so we have to minimize all of the other surrounding pieces in order to just focus on making sure our execution happens as quickly as possible. So there's this idea, what I've been describing so far is this idea of a cold start. And so what a cold start is you can see it downloads your code and then starts the container and then has to bootstrap and then finally launches the code. So there's a lot of optimization that we're going to talk about to optimize the cold start sort of penalty, if you will. And that way you can get to actually executing your function more quickly. So for instance, when you're loading these libraries, these dependencies, traditionally, when you load, let's say, an application, you load the dependencies at runtime, and it's not that big of a deal. If I wait 2 minutes, 5 minutes, if I even wait 20 minutes for my application to start, in the grand scheme of things, 20 minutes is not that big of a hit, because I'm going to have this long-running application that may be running for months on end, and I took a 20-minute overhead. It's not going to hurt that much. It's not a big deal. So I don't have to really optimize that area. But when you think of Lambda, in order to get to the function execution, if you waited 20 minutes or you even waited seconds, in a critical communications platform, it's not going to work, right? So you can't just afford to do a lot of those, well, I'll just load it at runtime or throw in and sort of not really care about my dependencies and not really focus on dependency management because I don't care about this initial overhead. Now you really are hyper-focused on that initial overhead. It matters so much that you don't want to sort of do some of those traditional things that you do. So instead of dumping libraries in, dumping dependencies in, be really conscious and really focused about what you're actually loading, and then be conscious about what is dynamically loaded at runtime. So instead of saying, oh, this is something that I'll just pull in at runtime, I'll go out and grab this library. If you did something really heavyweight, like reach out to a dependency API, pull down a library, loaded that in, all that overhead you're going to have to hit each time you execute that sort of cold start. And so the idea is don't pull that in. It's okay to bundle that in, bring that closer together, and make sure that you don't have these external dependencies so that you have the most control that you can have before launching this container. One other thing to think about in the cold start is the idea that with VPCs, you have to access your resource in a VPC. So there's this other layer. If you're having a VPC dependency, like I need to access my services hosted in my VPC, I have to attach a networking interface, an ENI, to get to that VPC. So again, yet another piece of overhead that's involved in this life cycle. And so that's something that's sort of unavoidable. You have to be able to get into the VPC, so I need an ENI. Again, if it's not a cold start, if you can leverage an existing container that you had just recently run, it's not going to hurt that much, but you don't want it to be something where you haven't run this function in a while and now you have to go out, attach an ENI, and then get into your VPC. It's just another layer. So on that note specifically, we have some updates. So traditionally what it was there's a local NAT that you would have for your Lambda function, and that would attach the ENI to the VPC. And it was unavoidable. This is just how you access your resources in the VPC. So this is something that we've had traditionally, and it works. But again, the cold start is there, and you can feel it. So moving forward, we're going to have this concept of essentially a remote NAT that you can pull from, and it's warm, it's living, it's a live ENI that you can bring in and attach to the function. So this is just something, this is an optimization on the AWS side that you'll notice as you are accessing resources within your VPC, they should get faster and faster because they're leveraging this new way of attaching the ENI behind the scenes. What this allows for is faster scaling, right? Getting those resources. Definitely lower latency because that ENI is sort of provisioned already and waiting to be attached to a Lambda function. And just easier to use overall, so you can try to minimize all of the complexities you were doing before to optimize that ENI attachment. Now it should be a lot easier for you to just attach that and move forward and access your resources within a VPC. So this is specifically for a VPC. If you had resources like attaching, or just accessing a DynamoDB or a Dynamo table, you wouldn't need to do this because those resources aren't living within the VPC. So just from a focus standpoint, this is for optimizations for accessing your, if you have a database in a VPC or something similar. So function runtime. So again, choose your dependencies and frameworks very carefully. So as you're going through, there are ways to optimize all runtimes, right? Whether you're using Java, .NET, whether you're using Go or Python, it doesn't matter. You can optimize all of them. But the key to remember here is that you want to be very conscious about what you're doing with those. So that JVM startup is something you're going to have to look at and think through. So you're going to want to use paradigms. So for instance, using a singleton design paradigm where you're instantiating an object once and then you're leveraging that existing object rather than recreating it each time is a really good way of leveraging an existing sort of either connection or initialization point without reinitializing. Interpreted languages in general are much quicker, but they're not necessarily faster overall. So it's, there are ways to optimize your traditional functions. If you have a Java-heavy application or a .NET-heavy application, you can certainly optimize those. It's just, again, thinking back to those dependency frameworks, dependency injection, how that's done and what's done at runtime, and how dynamic that is. If it's heavy and dynamic and requires a lot of CPU at initialization time, that's going to translate into a longer cold start. And then a good best practice is just to separate the business logic from the Lambda handler. And it goes along with sort of the theme. Your business logic in that execution lifecycle is what you're really trying to focus on and really try to get to. So you want to get to that as quickly as possible, and the Lambda handler, you put external from that so that you're not bundling that piece together. So the Lambda handler is something you sort of initialize outside of the function, and then your business logic, your core business logic, you'd put into the actual application function. So to see one thing in terms of container reuse, use that global scope wisely. So for functions that you've recently called without a VPC, they'll stay warm for roughly 5 minutes. Within a VPC, if you have sort of the ENI attached, that would be 15 minutes. And then again, don't load it if you don't need it, right? So if you have something that is going to be necessary, great. Use it, build it out, and make sure it's leveraged, but don't load all the extraneous pieces where in the past that wasn't that big of a hit. Now it's sort of a big penalty. So just be really efficient about what you're loading in. And then just to see an example of that separating the business logic from the function signature, you have the application logic, the business logic external, and then you want to have the handler separate from that business logic. This is a really good way to keep your the emphasis on your business logic and focus on getting to that as quickly as possible. So an example of tuning these, right? So after you've built that out, you've gotten really good and really confident about what you've put into your Lambda function, what you've loaded beforehand, you want to tweak it. And the control that you're going to get is a memory control in Lambda. So let's say you know that this workload is CPU bound or you know it's network bound, you're still going to want to tweak that memory because by tweaking the memory, you'll get additional CPU and get additional networking. But the only control that you have is that memory control. So don't, even if your function is like, oh, I don't need much memory for this, it's a CPU bound workload, that's okay. Tweak that memory and you'll still get better performance out of the CPU because you get better CPU as you tune that memory up. So an example of this, let's say that you have a Lambda function that's going to calculate all prime numbers less than or equal to 1,000,000, and you're going to run 1,000 iterations of this. If you do that and you use, let's say, 128 megabyte memory setting, it's going to take roughly 11.7 seconds, and for 1,000 iterations, 2.46 cents, which is cheap, but it's going to take a long time to run, right? So if I dial that up to 256 megabytes, I'm looking at half that time roughly for not much additional cost. A little bit of additional cost, but not much. If I go up to 512, I'm again bringing that CPU and bringing the time down to calculate those prime numbers with, again, a little bit of additional cost, but not as bad as actually the 256. And then if I go up to 1,024, I can see that the cost is down to, or the time is down to roughly 1.47 seconds. And actually, it's only a fraction of a penny more, right? So the idea here is that I tuned that up, and there wasn't a strict guidance on which one was going to perform best, which one was going to cost the most. So there's an analysis that you're going to do, and this is something you're going to want to do after you optimize fully, right? Because if you tweak this and then you take out a bunch of dependencies, you're going to have to retweak it. So the order of operations should be tweak or sort of build out your dependency structure how you like it, and then move forward with tweaking the memory allocation. And this one would be a CPU-bound workload to calculate those prime numbers, but by adding more memory, you're going to get more CPU. So some other best practices, know the limits in concurrency behavior. If you're building out a lot of Lambda functions and you're getting ready to deploy to production, you want to make sure that you know where those limits are and that you've stress tested the environment. This is a really good way to make sure you're staying in front of anything that's going to come along when you build out your serverless application. Because if you have a lot of onboarding or a lot of environments you're going to switch over, you need to know when you're going to reach those limits and make sure that you're either increasing those limits or finding a way to avoid hitting those ceilings. Again, minimize the package size is key. This is not only due to the dependencies and the extraneous dependencies, but also just the fact that you have to download that zip, right? So whatever you can do to make that smaller, just going to limit that initialization penalty you have to hit. Avoid using recursive code. So this is where I would go back and call that Lambda over and over again. That's not, again, that's something if you had a traditional application, that's okay to do, but in this world where you have that overhead and that overhead matters so much, you're essentially extrapolating that overhead many times. So you're bringing that overhead out by using recursion. So if you need to use something like that, think about different ways of leveraging that in either a single Lambda or Lambda like step functions and layers that we'll talk about. Definitely use environment variables to modify your operational behavior. So the environment variables give you a way to parameterize and add arguments without having tons and tons of Lambda functions that you're storing for different things. So Lambda functions should be very purpose-built, but it's okay to parameterize if they're used in several places throughout that application. Self-contained dependencies for sure. So rather than, again, reaching out to an external dependency structure to put yourself in grabbing that dependency at launch time or at load time, you want to bundle that together so that you can be very predictive and very consistent and constant on that initialization time. Delete large unused functions. So there is a 75 gigabyte limit, which is very high, but you want to make sure that you're not just storing a bunch of unused functions that aren't sitting there. It's more efficient to have a smaller footprint. And then we'll talk about this, but consider using layers. And so what layers allows you to do is leverage some existing libraries and things that you need and dependencies that you'll need without having to do a lot of copy and paste or a lot of the same function call over and over again. So layers, not necessarily from a performance standpoint, but just from a development standpoint, allow you to really leverage existing libraries and existing other methods and functions that other developers have built. And so you can essentially promote these layers, and it lets you separate and iterate faster on writing the business logic. Also, you can share these layers. So you can share them within your own AWS account, you can share them with your AWS organization, or you can share them publicly. And this is where things like some of the runtimes that are available, you will be shared publicly, and you can go consume those runtimes. So using Lambda Layers, so you'd want to put the common components in a zip and then upload it as a layer. Once you do that, these are immutable, and they can be versioned if you need to add updates, but they're immutable pieces of for your architecture. So the reason for that is if you have lots of functions and they're depending on these layers, and you go out and change those layers, that's okay, but those functions may need to leverage the previous version of the layer to stay compatible. They can do that, and if you actually delete the layer, the functions that are referencing that will continue to work, but you won't be able to create new Lambda functions that reference those deleted layers. So it's a good way it'll still sort of continue to support your application that you've built out. But as you're versioning these and as you're building more, you want to make sure that you stay as up to date with your functions as possible. You can reference up to 5 of these layers, and one of those can optionally be this runtime that we're describing. So for the runtime perspective, you can bring any Linux-compatible language runtime. A great example of this is the support for Ruby. So it leverages, if you want to use Ruby, you can totally do that. You would basically use the Ruby runtime API, and that's going to be done as a layer in the Lambda function. Other things like Erlang or other runtimes are also supported. Any runtime that's Linux compatible is supported. And you do this by leveraging the Lambda layer. So this is a really good way of reusing necessary pieces. And also, if you need to change something, you can change it in a single place. So it's a really good best practice to share not only the runtimes, but whatever other custom layers you might need. And then lastly, in terms of building out these applications, if you're nervous about HIPAA or PCI or other compliance needs, many of these serverless components that we're talking about, the services that we have, meet HIPAA and PCI compliance. So the ones that I described and discussed are all HIPAA and PCI compliant. And you can use, there's other compliance pieces there too, but the goal should be, this shouldn't be a deterrent. You can definitely build serverless applications and use them in not only critical communications platforms, but mission critical platforms meeting the compliance requirements. And with that, I'm going to introduce Mac from Spoke.
Thanks, Doug. So what is a critical communications platform? I think the best way to kind of describe what Spoke does and who we are is to walk you through a scenario. I want you all to kind of imagine you're sitting down on the couch after a large meal. You kind of felt like you maybe ate too much, feel a little bit heavy, maybe you feel a little short of breath. Not wanting to chance anything, maybe it's the flu, you decide to go into the hospital. So you walk up to the front desk, you describe your symptoms. All of a sudden, before you know it, you're surrounded by nurses and doctors. They're putting IVs in your arm. They're drawing blood. They are attaching pulse oximeters to your fingertips. They're running an EKG. The doctor comes up to you and tells you you're having a heart attack, specifically an ST elevation myocardial infarction, or as we call it, a code STEMI. They need to send you up into the cath lab, effectively an operating room, to put a stent in. The time that they have to get that stent in from when you walk in that door, we call it the door-to-balloon time, is 90 minutes. Anything longer than that, and permanent cardiac damage occurs. So time is absolutely of the essence. Luckily, in your case, it was a lot quicker than that. So let's walk through what happened behind the scenes. The moment they identified the code STEMI, they logged into a console. This console sent several messages out to phones, pagers, yes, they actually still exist, and mobile devices, specifically a couple of mobile apps that we've built. Those mobile apps allow the care team to collaborate. They allow them to share test results. They can look at your EKG. They can look at your blood work. They can kind of orchestrate everything to get you up into that cath lab as soon as possible. Now, this solution right now is in 1,900 different hospitals. So thankfully, we are reducing that time, that door-to-balloon time, throughout the country. Now, the average, without a critical communication solution, the average time to that door-to-balloon is 139 minutes. With this solution, the average is 68 minutes. So there's real impact that occurs from this. And we're going to talk about how we effectively transitioned to a serverless architecture. So the company decided several years ago to make the transition to the cloud. And a lot of it was driven by our customers. They don't want to be in the business of managing servers or physical data centers. They want to really be focusing on care. So as part of that, they invested in modern DevOps principles, infrastructure as code. So to just kind of quickly recap, what this means is that a developer will write some code, they'll check it in, that will be built as part of an automated build process, and then it'll be tested, a bunch of automated tests will occur, and then it'll be reviewed and merged into effectively a master branch or a release candidate. That in turn goes through a system test. That system test will go back into the build process as well. So all the teams that are building code are testing against what is effectively about to get out to production. So no one's lagging behind with their build pipeline. And eventually that will get deployed to production. Now, we deploy quite often to production. Launching to production is not a big bang deployment for us. We practice a lot of smaller incremental changes. And there's some really good reasons for that. One of the biggest is by reducing your batch size, you actually improve system reliability. And that's a pretty critical thing that we have found, that it's reduced our failed deployments. So we started, like a lot of companies, not going the serverless route. In fact, here's kind of what the original infrastructure looked like. We built a lot of stuff on top of Docker. So we had Docker containers inside of EC2 instances, inside of a VPC, inside of security groups, lots of alphabet soup going on. Behind an application load balancer, we were spending a lot of time turning knobs, building infrastructure, and honestly, it was probably the bulk of the time that we were spending. So there was a catalyst. Around about a year ago, a new VP of engineering came in, and he was kind of an AWS enthusiast. He had read all up on all the different services in AWS, and he challenged the fact that we were spending so much time building all this infrastructure and said, well, have you guys heard of Lambda? Yeah, we've heard of Lambda. Are you using Lambda? Yeah, No, not really. Would you like to use Lambda? Yeah, that's what we said. Well, he said, OK, well, why don't you try to take everything that you've built, this critical platform that you've built, using Docker containers, and make it serverless. Use Lambda, use Dynamo, open grazing. I thought that was pretty cool. As a developer, you get to play with a lot of new toys. Until they told us how long we had to do it. 3 weeks. I want to see the platform running serverless in 3 weeks. It doesn't have to be perfect, but I want to know that it's feasible. So after we freaked out a little, we ended up putting a small team together. Created a brand new AWS account. So before in the previous architecture, really the only people that had write access to our development environment was DevOps. In this case, developers are going to need to have access to the AWS environment. They're going to need to be able to write to that environment. They're going to need to be able to play. So we stood up a separate sandbox account. Okay? And we took our .NET Core-based application and began migrating it to Lambda. Interestingly enough, the first time we had something running was only a couple of days. We were a little surprised. And the bulk of the team didn't have any sort of AWS experience. Those first few days were really spent around learning AWS and how to use AWS. And a couple days later, we actually had some of the data persistent layer, a lot of the core database logic, migrated over to DynamoDB. And this is kind of our original architecture. It's fairly sparse. We made a lot of mistakes, which we're gonna talk about the blooper reel in just a little bit here. But what we had here is we took really just one of our stacks and put it behind API Gateway using what's called a proxy integration. So this is API Gateway. Whatever you get, just send it on to the Lambda. Now, this is not a recommended best practice. But for the purpose of getting up and running, it allowed us to kind of get up and running and experiment. And that, of course, was sitting behind DynamoDB. Now, when I talked about those first few days and we had .NET Core running, I'd like to show you exactly how we made that transition over to Lambda. Here's what it looked like before. Okay, so this is simplified. We had a couple of Docker containers. Nginx would kind of service the initial traffic. Behind that was the actual .NET Core stack with Kestrel, which is what serves all the HTTP requests, and that triggers the business logic. Okay? To convert over to Lambda, all we did was change that Kestrel layer over to an API gateway proxy function. Now, I know probably a lot of you have seen the slides where somebody just replaces a box and it looks really nice and clean and really easy, and then you get to do it and it takes 6 months. Been there, done that. So I'd like to actually show you the code. Here's what it looks like before. I mean, this is a little simplified, but here's what it looks like before. This is the entry point for a Kestrel-based .NET Core stack. And here's what it looks like after. As you can see, we just subclassed that right from the API Gateway proxy function, removed all the Kestrel logic, and we were off to the races. Now, I talked about the blooper reel, or the mistakes that we made along the way, and some of the best practices we learned. First one, I would say, is around IAM policies. Keep them locked down. Lock down early and lock down often. Okay? The default examples out there, they tend to use the Lambda full access, which allows you to have access to everything. You can access all the things across your account. But keep them locked down. So here's an example of this. How many have seen a policy like this? You know, you got Lambda star, log star, DynamoDB star, resource star. You can be honest. You can be honest. All right. Okay. A much better way of doing this, okay, is really around scoping it more towards what your service needs to do. Okay. Build those bulkheads, those security bulkheads. As you can see, we've locked this one down. This Lambda really only needs to invoke, put some log events, get a couple of records from Dynamo, and then we're really scoping that resource down to the nifty table. I don't know, probably hard to see out there. But again, lock down those policies early. It also has a nice side effect that if teams are kind of reaching into each other's databases like they shouldn't be doing, and they're not putting APIs in front of that or queues in front of that, it will identify that pretty quickly. Another one is your developers are going to have access to AWS. This is a lot of people that are going to have access to AWS. All right? There's a lot of opportunities for things to go wrong here. So use MFA. Make sure everyone is using MFA. That's not just for the console. You can do some really nice stuff with Simple Token Service, STS, so that you can actually scope that MFA access down to actual API and console level access. It's a great thing. It's a beautiful thing because eventually you're going to have to assume somebody's going to leak a key. We tell our developers that those access keys are nuclear launch codes. But you know that they're going to end up in a configuration file that somebody's going to upload to GitHub. I see some smiles out there. Yes, it happens. So have a plan in place to rotate keys. Use MFA. And the other thing I also recommend, which is not on this slide, is really use services like GuardDuty to monitor that developer account. All sorts of crazy things are going to happen. Your developer's going to experiment. This is just part of empowering them, but use GuardDuty to really kind of keep an eye on things out there. Another thing, which was one of our more interesting bloopers, was DynamoDB Tables. So who here has used DynamoDB? All right, a lot of people. Who here, when they first started using DynamoDB, treated it like a relational database? Again, honesty's appreciated, because we did it. A lot of times you find out that, not necessarily a relational database, but everyone creates a separate table based on the object. So we've got a user table, we've got a group table, we've got a department table, and then we kind of link through them. You know, we luckily have considered eventual consistency in this model. But we did this, and what really kind of woke us up was the advanced design patterns for DynamoDB reInvent video. If you're using DynamoDB, watch that video. I mean, again, it's advanced design patterns for DynamoDB. That opened our eyes and realized that we're doing quite a few things that are not right here, that are not a best practice. So we ended up migrating to a single table. As you can see here, everything is all in one table. So each of our services has one table. Our primary keys are generic, so they represent typically a unique identifier. There's a sort key that we can that is typically scoped to the user. So maybe with Bob, it might be Bob's name. And in a lot of cases, we also use ragged rows in this. So obviously, the row for rapid response will be different than the columns for rapid response will be different for the columns for the user. In this case, Bob. Okay. That way, we can build global secondary indexes off of that. So the key point I tell our teams is that if you're trying to decide between Dynamo or Aurora, ask yourself a couple of questions. Do you know how you're going to be accessing your data? If you do, then use Dynamo. Is it transactional in nature? If yes, then you may want to consider a SQL-based database like Aurora. Or if it truly you don't know the answer, you're going to be doing some analytics on that, then you may want to consider a relational database like Aurora. Another key thing that, getting kind of down to the critical communications point of this, is around orchestration. How do we deploy all of this to production? We've got a lot of different teams that are making a lot of changes, and they're not all lockstep. Things are merging in throughout the time. One service updates, another service updates. How are we orchestrating all of that? Well, we end up having to create a new utility called Bootstrapper. What this does is this leverages CloudFormation, but in a different way. We originally tried nested templates, but the templates the base kind of parent template in that case is immutable, and we couldn't do that because we're constantly changing our infrastructure. So in this case, Bootstrapper brings in a set of templates. So each of our services has a template that they publish. This is mostly a CloudFormation stack, but there's some additional data associated with that that advertises the information that it needs from the various services. Okay? That generates a CloudFormation stack that deploys, in this case, initially the first parent stack, which is our common services. This will be things like Route 53. All the services are using Route 53. But they also might need to know that information about Route 53. So that gets passed through as part of the CloudFormation parameters. So the other stacks can then update with that information. So we can update any one of these stacks without having to redeploy the whole system. So we can do these smaller incremental deployments throughout our system. So this was a big key piece to making sure that we're not taking our system down for updates, that this system is always operational. I'd like to also kind of walk you through our reference architecture. Now, this here is not completely what every one of our services looks like, but this is the foundational layer that a lot of our services build upon. So I want to start you out with the user comes into the system. It looks up the DNS entry in Route 53. The front-end code has been deployed to Amazon S3, which, of course, seeds a CloudFront distribution. That CloudFront distribution, of course, loads into the user's browser. It's not always a browser either. It's also a mobile app. That will make a call out into API Gateway. That API Gateway is going to then hit that services Lambda, okay, which, of course, uses DynamoDB with a single table. It'll log any of its logs or metrics to CloudWatch, which I can't stress that enough. Use CloudWatch. It's a fantastic tool. And from there, we'll return the call back to the user. Now, this is great, but what about other services? We talked about we have multiple services in our stack. One of the things we always talk about is building bulkheads. And part of what that means is that, let's say we're updating one of these Lambdas, things are changing, they're churning. Okay? Even though it might be a couple of milliseconds during the update, we still want to make sure that we're not dropping any traffic on the ground. So there's other services that are going to need to communicate with this Lambda. So what we make use of at that point is a combination of either SQS or Kinesis or both. So we use simple queue service when it's, say, it's a one-off event. You know, it's a single event you can just kind of publish and subscribe to. In some cases, we've got streams of data that are coming in, and we make heavy use of Kinesis. These, in turn, end up in what we call an event Lambda, which writes directly to DynamoDB. It actually doesn't trigger the services Lambda. And that, of course, also uses CloudWatch. What is nice about this is we can take one of these services down for, you know, if we really wanted to, for a minute or two or a couple of minutes, which we wouldn't do, but we can take them down. And the only thing that happens in that case is a queue starts to back up. We bring that Lambda back online, and then the Lambda can service all of that traffic. So one point I want to make as well with this pattern is it's critical, it's absolutely critical that your services Lambda and your event Lambda share the same data persistence layer, whether that's through Lambda Layers or through a shared library. So what this means is that those things are in lockstep, so you can avoid data inconsistency within DynamoDB. So let's say you update your services Lambda and you don't update your event Lambda and that data persistence layer changes, you're going to be in for a world of hurt. You're going to get a lot of data inconsistency in Dynamo. So to kind of recap here, Lambda really allowed us to move quickly. In fact, going from that first runway to where we actually deployed a serverless production infrastructure, and this means 0 EC2 instances, was only 9 months with our team. The other side of this is you're going to need to empower your developers when they do this. Your developers are all going to have to become AWS experts. Whether that happens organically or through training material, they're going to have to become AWS experts. They're going to need an AWS account to kind of play with, to experiment with. Keep that separate from your prod account, just a little bit of advice. But they're going to need that account. So you need to put proper controls around that where you're using MFA. You're providing proper guardrails for your developers when they're using that account, and you're watching it with guard duty. Another nice part of this is infrastructure should always, always, always be done as code. So when things migrate from that sandbox account to that development account or that prod account, it should be done as code. You shouldn't have to have somebody in DevOps having to go in and turn a knob in a development account to make something get through to prod. That should never be done. Review your resources as well on a regular basis. Now, Lambda makes this a lot easier. One of the challenges sometimes with EC2 is you might have an EC2 instance that's out there and it's been running for like 3 months and no one knows what it does. The moment you shut it down, all of a sudden everything breaks. The nice thing about Lambda is that the ephemeral nature of it is a lot of times we can remove a Lambda resource as part of a cleanup operation, and it's kind of a non-event. But make sure your resources are getting cleaned up. Developers will leave resources hanging around. And again, I've already emphasized this before, but keep IAM locked down. Always use MFA and assume a key is going to leak. And finally, AWS is a big place. It's a really big place. I think everyone in the room knows that. But leverage all of the AWS educational material out there, especially the reInvent videos, the various sessions here, and a lot of the blog articles. We constantly follow those, and we constantly report back to other teams around best practices that we've learned. Thank you very much. Does anyone have any questions?
Step up to the mic.
How do you maintain portability between cloud environments? So do you have a plan in case something happened to AWS that you can go to another cloud like Azure? How do you worry about that?
Oh, so being cloud agnostic. So one thing I didn't really talk about here was that huge Docker architecture that we had was because we were trying to originally be cloud agnostic, to be honest. You will often become your own worst enemy by trying to be cloud agnostic, to be honest. All right? You're going to spend a lot of time building infrastructure upon infrastructure upon infrastructure. The more likely failure point is going to be your own infrastructure, just in my own experience. So in the case of portability for the Lambdas themselves, a lot of times we run those containers locally on our dev environments inside of Docker containers. So developers want to be able to just kind of step through and debug code. We'll run those as Docker containers locally. So we still maintain those two entry points, but not with the intent of being cloud agnostic. Just because, again, it's a very difficult path to go down. And I think it actually has more risk than most realize. Yes?
Can I give you the mic?
What do we use to deploy our serverless service? Yeah, so we make heavy, heavy use of CloudFormation, and we also created Bootstrapper, which is, it's actually not a huge application. It's a Python script that we have that deploys the individual stacks and keeps everything synchronized across them. So another key point on that is those really work for deploy time concerns. For runtime concerns, you may also have to leverage some sort of service discovery, such as Cloud Map as well. Any other questions?
Thanks, guys.
All right, well, we'll be down front if you have any more questions. Thank you very much. And please complete the session.